All right, guys. Hello and welcome to Math with Miss Leslie video style. Okay, just kidding, but for real though. All right, this is video number 1 of our exponential functions and logarithmic functions unit. Today we're going to do exponential functions intro. All right, bear with me. I haven't done these videos since COVID, so hopefully they turn out okay. We shall see. All right, so I'm going to go ahead to OneNote now. Okay, there we go. Now I'm just got to minimize this screen. I can't see myself anymore, but I think you guys still can see me. So here we go. Exponential functions introduction. So truthfully, guys, the first half of this unit is really just what we were doing in our last unit. Last unit, sequences in series, is a great introduction to exponential functions because essentially exponential functions are just geometric sequences, function style. And we're going to talk about the two main differences between geometric pattern as a function versus the geometric pattern as a sequence. All right, and there are two kind of main differences that kind of come into play. So first off, let's look at this pattern. So we have a 2, 4, 8, 16, 32. We want to make an equation that would help us find the next term and future terms. All right, so just thinking about what we did last unit, we're going to see if we can find a pattern. I've already kind of spoiled it, and I said that this was going to be very similar to our geometric pattern. So we're looking for something that's going to multiply over and over and over again to get the next term. This is a simple one. We've done this example before, right? So 2 to 4, we're multiplying by 2. 4 to 8 is a multiply by 2. 8 to 16, 16 to 32, we're just multiplying by 2 over and over. This is what makes this sequence a geometric. Sorry about the pen. It, for some reason, is skipping a lot. What are you going to do about it? All right, so it is a geometric sequence. So we can then take what we know about geometric sequences and we can make an equation. So we would say, all right, a sub n equals, all right, our first term is 2, our common ratio is 2, and we would raise this to the power of n minus 1. And that is our equation to find our future terms. We call this the explicit. Yeah, I don't know why the pen is writing like this. I don't know. Explicit. That's what that says. All right, this is our explicit equation. Now, this is a great equation, all right, but there are two main things that are going to differ between this explicit equation as a sequence versus our functions kind of explicit equation. All right, so first off, let's talk about what it means to be a function. All right, so I know that we did a functions unit way back when, all right, but functions have to do certain things, right? So one, they have to have unique x values for each of the y's, right? You can't repeat your x's, right? So that's one of the main things. Everyone always remembers that one, right? And we know about the whole vertical line test. You can't cross a vertical line more than once. But another one that people don't really talk that much about is that functions are continuous. All right, that doesn't mean they don't have jumps. Like think about rational functions. We know rational functions have asymptotes, they have holes, right? So there are jumps in the graph, but regardless of the jumps in the graph, at the end of the day, if you look at the two ends of a function, they're approaching something. They're going to infinity. They're, they have some kind of end goal, right? They might be approaching a horizontal asymptote, right? But overall, it's one continuous thing from left to right. Ultimately, like I know it looks weird, but ultimately over time, if you plug in really giant x's, the function has an end goal. It's either growing exponentially in one direction or it's, going to a specific value. Sequences, on the other hand, are not functions. They're not continuous, right? Because we know what's happening at term number 1 and we know what's happening at term number 2, but we don't know what's happening between term number 1 and term number 2. It's not continuous. We don't know what's happening in between there, right? Because sequences don't have terms like 1.5. All right, so this is something that we would say is not continuous. All right, so one of the things we're going to do when we're looking at functions is we're going to get rid of the fact that n can be any number. N is all real numbers, all right? Whereas when we're dealing with sequences, n needs to be an integer, and it needs to be a positive integer, right? You can't have negative terms of a sequence, but you can have negative values, right, in a function. So that's one of our main differences. All right. Now, the main thing that this is going to kind of change for us is our starting value. All right. So instead of saying that we're starting at our first term, really with functions, we're going to start at 0. We're going to start at our 0th term of our kind of sequence. So this changes the equation just a little bit. All right. So first kind of real difference that we're looking at, right, starting to transform that geometric explicit equation into kind of a function equation. I don't know why it's writing like this. All right, so our first difference, right, is that we are starting at 0. All right, so our function starts at 0. All right, which changes our equation a little bit. So obviously this is a function now, so we're not going to use a sub n, which is our kind of sequence notation, right? We're going to use y, right? Y equals. So we've got y equals, right? And instead of our number out front being a sub 1, it's kind of going to be our 0th term, our starting value. And to do that, we're just going to use a. Right, a is representing our start value, all right, which is basically our 0 term, right? What's happening at 0? So our 0 term, all right? And then instead of using r to represent our common ratio, we are going to use b, which represents our base number, all right? But it's the same function, all right? So times, we say b. This is essentially your common ratio. All right, but when we're turning it into a function, this is referred to as the base number. All right, but it has the same feature. It's what we're multiplying by to go from one term to the next, one thing to the next thing. All right, and the last thing is that our exponent for our b is just going to be x. It's no longer going to be x minus 1. The reason why in our sequence it's n minus 1 is because we want to not apply the base number for the very first term. So when we look at this in our example, we have 2, right, is our starting value. That was a1, all right, but if we're starting with our 0th term, all right, we want that first exponent to end up being 0, so we don't need to subtract 1. If we had 0 subtract 1, it would then be a -1 exponent, and that's what we want. We want it to be a 0 because we know anything to the power of 0 is 1. So if we're dealing with functions and our starting term is our 0 term, then our exponent only needs to be x, not x minus 1. All right, but x still kind of represents the term number that we're on. All right, it's also going to represent like how much we're counting by. Right? We're going to do a lot of word problems. All right, so if we're doing a word problem and it says like we're applying interest every month, then x would be how many months have gone by. So x is still like what we would call our counter, right? It's what term or how much time or whatever it is that we want. All right, so I like to refer to the x as like our counter. It's what we're counting by. Could be term number, could be months that have gone by, whatever the problem wants us to do. It's our counter, what we're counting by. Okay, so there's our exponential function. So there's our equation that we're going to be using. Now, I said there were two main differences. So first, it's a function and we're starting at 0, which changes up the equation a little bit. The second difference has to do with our base number. Now, I said before, functions need to be continuous. In order for our sequence, which is now a function, to be continuous, you have to put restrictions on what you can have as your base number. Specifically, you have to have positive base numbers. You cannot have a base number that is a negative number, because think about what that does to your function, right? So say you have a base number of -2. So if you have base number of -2, then if you were doing a sequence, you would have like a positive number, then a negative number, then a positive number, then a negative number. Because every time you take a negative number and you raise it to an even power, you would get a positive. If you take a negative base number, you raise it to an odd number, you get a negative. So what you end up with is not a continuous function, it's an oscillating thing, right? It's bouncing back and forth between the positive and the negative answers. This is not continuous. So our second difference is that we do have to specify our base number cannot be negative. All right, so let's erase this. I meant to write difference number 2. Difference number 2, the base number must be positive. Base number B must be positive. Okay. Can't be negative because then it's not a function. All right. And some of you guys kind of figured that out when you were trying to convert your exponential situation you had to logs in order to solve. You notice that if you had a negative base number, your calculator would say error. That's because that's not a function. So we have to restrict it to say that our B values must be positive. Okay, so we're going to start by figuring out percentages. So a lot of the problems we're going to deal with have percentage-based numbers. So we're going to take a look at what that is. All right, so here we go. Given the percent increase or decrease, write an equation that represents the given scenario. Okay, so we had word problems that were like this. They had like the bear population is increasing by or decreasing by 10% each year, right? And a lot of you guys had questions on how do you find that multiplier, that common ratio, right? That base number for your exponential function. All right, so here we're going to take a look. So if we're increasing by 40%, all right, and our starting value is 15. An increase means we're going over 100%, right? So when we're doing this, first what we want to do is we want to convert our percentage to a decimal. You can do this by taking 40 and dividing it by 100, or you can just put the period behind the 0 and you just move your decimal places 2 positions to the left, right? Either way, you end up with your decimal conversion. So 0.4 is 40%, all right, just written as a number. All right, so we have 0.40. Now, what we want to do is if we're starting at 100% and we're just increasing by 40% each time, we take 100%, which as a numerical, just normal number is 1.0, and we're going to add, because we are increasing, the 0.4. All right, that is a 0.40. Use your imagination. So our common ratio, our base number, is going to be 1.40, or just 1.4. All right, so then to write an equation, we have y equals, our starting value is 15. All right, our common ratio, or our base number, 1.4, and then it would be to the power of x. So there's our equation. So when we're increasing, all right, we always want to start by taking our percentage, converting it to a decimal. If it's an increase, you're going to take that 100%, that 1.0, and you're adding on your percentage as a decimal. All right, now move on to decreasing. So this one is a decrease of 25%. So same concept, we're going to take that 25%, and we're going to convert it to a decimal. That would be 25 over 100, which is just 0.25. All right, now since this is a decrease, again, we're starting at 100%, so 1.0, that's a decimal, right, 100%. And since it's a decrease, we're going to subtract that 0.25. All right, so that's going to give us 0.75 as our base number, what we're multiplying to get each of our kind of sequential terms, if you want to think of it kind of paralleling it to sequences. All right, so then our equation would be y equals, it says our starting value is 3, so we have 3 out front, and then we have our 0.75 as our base, and then we're going to raise that to the power of x. All right, so there's a decrease, right? So increase, you're taking that 1.0, you're adding your percentage. A decrease, you're taking the 1.0, you're subtracting your percentage. All right, so next up, we've got, here's an equation. Determine your percent increase or decrease for each of the following. All right, so number 1, we have our number out front, our 5. All right, that's our starting value. I know it doesn't ask you to do that, but it's not a bad idea. All right, so our starting value, right, A in this equation is 5. All right, and then our base number is 1.36, and I want to know what percentage increase or decrease did we have. So we're doing the same thing we did above, but we're doing it in reverse. All right, 1.36. This is definitely an increase because we're over that 100%, that 1.0. So we want to figure out by how much. You're just going to take your 1.36 and you're going to subtract off the 1.0. I know this seems super easy, but my Amazon order. Anyways, I don't know if you guys could see that or not. I think you could, but it's fine. All right, 1.36 minus 1.0, and we get 0.36. All right, so that's the difference that we are away from 100. Now what we want to do is we want to take this value and we want to convert it to a percentage. All right, so if we had to divide by 100 to get it from a percent to a decimal, then we would do the reverse of that. We would multiply it by 100 to get it back to a percent, and that gives us 36%. All right, so this problem had a 36% increase. All right. Cool. All right, next. All right, we have 9 out front. We have this 6 and our parentheses raised to the power of x. So we know that our starting value is 9. Again, I know it doesn't ask for that. All right, and then our base number is 6. So remember, we're starting at 1.0. So if it's above 1.0, it's an increase. All right, if it's below 1.0, it would have been a decrease. So this one is 6. So if we're doing the same kind of logic and we're starting with like the 6 and we're subtracting away the 1.0, all right, that gives us 5, right? 6 minus 1 is 5. All right, and in order to find our percent, we do the same thing. We're just going to times it by 100. All right, and we get 500%. So this is a 500% increase. Pretty big one, right? 500% increase. All right. Moving on to the next one. So this one's going to require you guys to use some of your exponent properties. All right, so you see how in our exponent we have a -2 there? When you're doing your exponential equations, you do not want to have a number in the exponent. I mean, you can do that, like, right, we're going to learn how to graph with numbers like that in the exponent, but it doesn't tell us what our increase and decrease is going to be. So the first thing we have to do is we're going to need to take this 2, this -2 that's in front of the x right there, and we need to apply it to the 10 that's in the parentheses. So I'm going to go ahead and rewrite this. All right, so we've still got the 3 out front, 10 to the power of -2. All right, so we're essentially moving the -2 into the parentheses. All right, so we're just separating that. And you can do this. Our exponent rules say raise a power to a power you multiply. So we're just kind of splitting it up. But remember, multiplication can be in any order that you want. So I'm really just kind of separating the -2. All right, and then I'm going to apply that exponent. 10 to the power of -2 is the same as 1 over 10 squared. And 1 over 10 squared, that would be 1 over 100, which is, as a decimal, 0.01. All right, so I just ran through some exponent properties. So this now is kind of simplified, and this is now what's going to allow us to figure out our increasing and decreasing. So first thing I know is this is definitely decreasing because it's below 1.0. So I know that I've got a decrease. So what I'm going to do is I'm going to take that 1.0, I'm going to subtract away my base number that I've got in there, so that 0.01, and that's going to give us 0.99. All right, now that is my decrease as a number value. So what I need to do is I need to turn that into a percentage. So I'm going to multiply it by 100, and I have a 99%, and it's our base number was below 1.0, so that means this is a decrease. A 99% decrease. That's a really good sale if you're shopping, right? Cool. All right, so that's how you can figure out your percent increase and decrease when you are given an equation. You may have to use exponent properties like we did on number 3. Big things to remember are if you're above 1.0, it's an increase. You need to subtract what your base number is from 1.0 and then multiply that by 100 to get your percent increase. If you're dealing with a number as a base that's below 1.0, it is a decrease. To find it, you're going to have to take that 1.0, subtract away what your base number is, take that value like we did in number 3, which was we ended up with 0.99, times it by 100, and then you have your percent decrease. All right, and I think this is our last section. So making an equation given a table. All right, and you guys did stuff similar to this. This is essentially looking at a sequence, all right, to where you're trying to find that common ratio each time. I don't have a calculator, so I'm going to pause you. You guys are not even really going to notice. I'll be back really fast. Okay, got it. All right, now we'll just minimize this again. I needed a second monitor so you guys couldn't see this and I didn't have to minimize it, but alas, I couldn't find the cord. So that's where we're at. Okay, so here we have our table of values. Now, again, think of this like a sequence. What you need to do is figure out what is that common ratio going from one term to the next. So that's what we're going to do. All right, so we've got 1.5 and we're going to divide it by 1.875 and it gave me 0.8. 1.2 divide 1.5, 0.8. All right, 0.96 divided by 1.2. What do you know? It's 0.8 again. All right, there's some lag, all right? So it's gonna pop up. All right, but essentially what we've got is we have a common ratio or common multiplier of 0.8. This is going to be our base number. All right, so B equals 0.8. Okay, I think it's, yep, we're back recording. So I just paused because the lag was really bad. Okay, you guys don't even notice. You didn't have to pause. Okay, so anyways, we have a base number of 0.8. Oh, I need to get this out of the way. It's because it's confusing to look at. Okay. All right, base number 0.8. All right, now we also know what our starting term is. So remember, this is a function. Our starting term is going to be our 0, right, when x is 0. So right here, when x is 0, all right, we have a y value of 1.5. This is our A, our starting term. All right, so putting this, there we go. All right, putting this into an equation, we have y equals our starting term, 1.5, our base number, 0.8, our exponent of x. All right, so there's our equation. Now the second part says give the percent change found in each table. All right, so our base number is 0.8, so we have to ask ourselves first, is this increase or decrease? It is a decrease. Hopefully we're all thinking that, all right, because 0.8 is smaller than 1.0, so we know that it's a decrease. All right, we just now have to figure out what is it decrease by. So we take our 1.0 and we're going to subtract that 0.8 and that gives us 0.2. All right, there we go. So we have 0.2. Now remember, we're going to take that 0.2, we're going to multiply it by 100, and that's going to give us our percent decrease. So that is a decrease of 20%. I don't know why I put an equal sign there. Decrease of 20%. So we have our equation and we found our percent change in our table. Perfect. Now, the next one is the same concept, but it's a little different. All right, so you guys remember when we did the problems and it was, I'm giving you the 4th term and the 7th term, find the equation that represents this, or find the future, whatever future term, find the 10th term or whatever the question was. So I didn't give you every term in the sequence, I kind of just gave you a little bit. This is the same concept, all right? So if we take a look over here at number 2, it gives me the -2, and then it jumps to 1, and then it jumps to 4, and then it jumps to 7. All right, well, what we need is we need just like the sequential terms. We need to figure out what's the difference between term 1 and term 2, not necessarily what's the difference between terms 4 and 7. So we can kind of think of this as like this is -2. We don't know -1. We don't know 0. We know term 1, and that is 10. So this is term number 1, and it's 10. Term number -2 is 0.64. Ooh, this pen. I don't know why I'm skipping like that. Okay, so first we're going to say, okay, well, we took one number and we multiplied once, twice, 3 times. All right, so if we took some number, we'll just call it x, or actually, more accurately, we're going to call it b. All right, b to the power of 1, 2, 3 is whatever 10 divided by 0.64 is. All right, so b cubed is whatever 10 divided by, let's slide ourselves over, 0.64 is. All right, well, what is that? 10, math, enter, enter. All right, that is 10 over 0.64 is 125 over 8. So we have b cubed equaling 125 over 8. So if we want to know what b is, we have to cube root. So b, cube root of 125 is 5, cube root of 8 is 2. So our common multiplier here is 5 halves, which is 2.5. Oof. Sorry, guys. That is really writing terribly. All right. So 2.5 is our b value. All right. Great. The next thing we need, though, is our starting term. And our starting term is going to be our 0 term when x is 0. And we don't have that, but we can find it. We just need to go back by 1. So what I'm going to do is instead of multiplying by 2.5, I'm going to take 10 and I'm going to divide it by 2.5. All right, and that gives me 4. So this would be my 0 term. It's not a bad idea to just kind of keep going and check your answer. So to keep dividing by 2.5. And see if you get back to that 0.64. I did, right? I ended up with my 4, and then before that got me 1.6, and then if I divide again by 2.5, I ended up with 0.64. So it does seem like my base number is correct, and I also now have my starting term, which is my 0 kind of term of my sequence. So there's my start. So here we go. We can make this into an equation now, right? Our starting term is 4. Our base number is 2.5. It's really writing that. All right, our base number is 2.5, and it's to the power of x. Now, one thing I would recommend doing is now that we have our equation, maybe plug in these future x values to make sure that they check out. So what I'm going to do is I'm going to take my calculator and I'm going to type in 4 parentheses 2.5, and I'm going to do it to the power of 4. Make sure I get 156.25. And lo and behold, I got 156.25. I don't know if you could see that, but you guys know how to use a calculator. Right, so it seems like my equation checks out. All right, my b value is that 2.5. So here's my equation. Now the last thing it wants me to do is to figure out my percent increase or decrease. So since this is above 1.0, I know that it is an increase. All right, I'm going to take that 2.5. I'm going to subtract off 100% to see my difference. That's going to be 1.5. And then I'm going to multiply by 100. So I have an increase of 150%. And there we go. There's our problem. Sorry, there's the work. Sorry. Okay, so that is our introduction day for exponential functions. Now you guys should work on the practice problems that go with this. All right, and I'm going to go make the next video in our saga of math videos. All right, hold on. I'm going to awkwardly try and find the button. I found it. All right, guys, have a good one. Until next time.